La donna mobile, qual più al vento, mutua da certo di pensiero.
That was feedback. Uncontrolled feedback. Feedback run amok. Very undesirable indeed. But feedback, properly analyzed and controlled, becomes a powerful tool in the hands of the modern engineer. Feedback can accurately, efficiently, and reliably govern guidance systems, servo systems, power supplies. The list of applications is limitless. Still, the consequences of feedback incorrectly analyzed or controlled can be very serious indeed. Incorrectly controlled feedback costs government and industry millions and millions each year in decreased efficiency, downtime, and lost sales through customer dissatisfaction. Until very recently, feedback analysis and control methods were inexact, depending on lots of effort-wasting trial and error. Modern technological advances demand a faster, more reliable, and more efficient method of analyzing and controlling feedback. Let's look at a typical feedback control situation involving a human instead of a machine. This young lady is in the process of learning how to drive a car. She knows she is supposed to keep the car between the center line and the shoulder of the road. She turns her steering wheel back and forth, trying to stabilize her car. But she can't determine just how far or when to turn the wheel. So she weaves back and forth. Unlike a machine, she knows that she is doing something wrong. But let's assume for a moment she is a machine and is incapable of realizing that she is making an error. We'll trace her car's path and compress it a little to make it easier to visualize. As she was proceeding, she should have turned her wheel slightly here, but instead she turned it late and then overcorrected. She did the same thing here, and here, and again here. She is experiencing what engineers will recognize as insufficient phase margin, with the phase lagging more and more with each turning of the steering wheel. Her delay in turning the wheel resulted in excessive phase shift and positive feedback. Although, as we can see, positive should not be construed as synonymous with desirable. This is a diagrammatical example of negative feedback. The error diminishes until it disappears altogether. So, a negative feedback situation is good. A positive feedback situation is bad. But as you can see in this diagram, our driver had to do a lot of correcting back and forth before she got her car stabilized. For every bend in the road or gust of wind, she would have to repeat all those motions to stabilize her car. Perhaps a single uncorrected adjustment directly to the desired path would have been best. Or would it? It might take much too long to achieve stability. Our driver needs her loop optimized. Optimizing a closed loop means finding the appropriate amount of phase margin and the correct crossover frequency for the fastest correctional response. Previously, finding these parameters was a hit-and-miss proposition, taking days, weeks, even months of trying one combination of capacitors and resistors after another until an acceptable, but not necessarily optimum result was achieved. There clearly was a need for a better, more efficient method. Venable Industries, already a leader in the automated welding and servo systems industries, accepted the challenge. After exhaustive R&D and assimilating volumes of input from engineers, Venable's team of engineers and designers came up with that better method, the Venable method, and it exceeded even their own performance expectations. Let's take a diagrammatical look at a feedback control system and its components. For the purpose of clarity, we will divide feedback control systems into two main functional elements. The first element is the power processing section, or what is often called the plant or modulator. The modulator could be the switching regulator portion of a power supply, or it could be a hydraulic, pneumatic, or electromagnetic position control system, or most any other regulating device. The second functional element of the feedback control system is the error amplifier. The error amplifier allows the loop to be closed by comparing the modulator output with a reference input and amplifying the error signal back to the input of the modulator. The combination of these two, the modulator and the error amplifier, forms a closed loop. Modern engineers, utilizing a Venable stability analysis system, are able to not just close, but optimize any given loop in minutes with accuracy and reliability. A breakthrough for engineers? Absolutely. But with the Venable system, that's just for openers. It will provide measurement and modeling capabilities from 0.1 millihertz to 100 kilohertz. That's versatility. But that still isn't all. It will also determine and plot the transfer function of filters, determine phase characteristics, Q factor, attenuation, and measure and plot parasitic response. It is affordable, menu-driven, very user-friendly, and a complete turnkey frequency response analysis system. In fact, it is virtually a complete circuit design center. And that's why you know that the Venable system will be used. You would have to get at least 4 separate pieces of equipment to do what one self-contained Venable system will do. And those 4 still couldn't optimize a feedback loop. The Venable system is based on a digital Fourier integral gain phase meter and is supported by the industry standard IBM PC microcomputer. And it has been designed for easy application to any industry: electric, mechanical, electronic, electrochemical, servo and electromechanical, and electro-hydraulic, to name just a few. If we were able to use the Venable system to compensate our young driver like a machine or electronic device, that is, optimize her loop so she would make precisely the right correction at the right time, we would only have to analyze her driving capabilities, compensate for her errors, and place her behind the wheel again. Her driving performance would be virtually flawless. But of course, only machines can be modified or compensated for ultimate performance. And there are only 2 ways to compensate a machine. The old way, which is trial and error, with the accompanying losses in accuracy and reliability, not to mention days or weeks of drudgery. Or the new way, by the path of understanding through accurate measurement and analysis, which allows the modern engineer to optimize the loop, not just achieve stability. Although their numbers are diminishing rapidly, some engineers, even highly experienced and capable ones, are still resorting to the drudgery of outmoded trial and error methods for closing loops. Even though this Venable system provides an infinitely more efficient analysis and design method, is readily available, more reliable with a 4-year track record of success, and is substantially more cost efficient, even in the short run. Using our feedback control model, you will recall that there are two main functional elements in a feedback control system: the plant or modulator and the error amplifier, which amplifies the error signal back to the input of the modulator. These two, when connected and operating, provide a closed loop. The gain around this loop is the product of the gain of the amplifier and the gain of the modulator. If we express these gains in decibels, which are logarithmic, the gain of the loop is the sum of the gain of the amplifier and the gain of the modulator. When gain is expressed in dBs, graphic analysis is simplified. The gain around the loop is the sum of all the gains around the loop, and the phase shift is the sum of all the phase shifts around the loop. The Bode plot graphically displays the transfer function, that is, the output divided by the input. The Bode plot is a graphic representation of logarithmic gain and linear phase shift versus logarithmic frequency. At some particular frequency or frequencies, the total phase shift around the loop will equal 360 degrees. This makes the returning signal indistinguishable from the original signal. If the total phase shift around the loop is 360 degrees at the same frequency at which the gain is 1, or unity, the loop will oscillate. For a feedback loop to be stable, the total phase shift must be less than 360 degrees when the gain is unity. The loop will also be stable if the total phase shift is 360 degrees and the gain is less than or greater than unity. When the gain is unity, the phase shift must be less than 360 degrees. The actual amount less than 360 degrees is the phase margin. But as we have discussed, just stabilizing a loop does not mean it has been optimized. The phase shift and gain identified on a Bode plot of a modulator can be utilized by the modern engineer to determine optimum crossover frequencies and phase margin for any feedback control system. This is a Bode plot of a loop that is unconditionally stable. Phase lag is increasing with frequency. When the loop gain is unity, the total phase shift is less than 360 degrees. The difference between the phase lag and 360 degrees at the frequency where the gain is unity is called the phase margin. At some higher frequency, the total phase shift reaches 360 degrees. At this point, the gain has fallen below unity. The amount the gain has fallen below unity is called gain margin. Phase margin and gain margin are an accurate measure of how stable a system is. That is, how far away it is from oscillation. High-resolution graph paper is used in the Venable system because very high resolution is absolutely essential for true loop optimization. There are other advantages with graph paper as well. It is easy to incorporate into reports. It can be saved for reference or studied at different times by different people. On the left of the graph paper, decibels of gain are indicated. On the right, degrees of phase. Across the top, on the x-axis, logarithmic frequency is indicated. The center line represents both 0 dB, or unity gain, and 0 degrees of phase shift. With the Venable system, a junior engineer or technician working under the supervision of an engineer can effectively and efficiently optimize loops in minutes, saving valuable engineering hours for more productive and creative effort. The high-resolution graph paper is inserted into the plotter. The plotter can, incidentally, be calibrated in a moment. And, if desired, it will even plot on reactance frequency graph paper. That's just one of many exclusive Venable system features. After power up, the menu will direct the operator what to do next. She makes sure the time and date are okay. She types T for the title block and puts in her title. She types A to go to her analyzer. The analyzer menu appears. She keys in the correct control voltage to get the appropriate output voltage. She hooks her system up to the modulator she is going to test and hits J, which turns on her stimulus, the AC test signal. She verifies the test connection to her circuit and hits J again to start the plot. Note that the title, date, and time were automatically annotated by the plotter. The red graph indicates gain in decibels. The blue, phase shift in degrees. When she hits K, the K factor menu, which will provide the closed loop, appears on the screen. She selects the chosen configuration of error amplifier. She enters the desired crossover frequency, in this case, 3 kilohertz. The modulator gain of -1 dB at the desired frequency of 3 kilohertz is entered, and so is the modulator phase lag at 3 kilohertz. She enters the desired phase margin of 60 degrees and the input series resistor 100K ohms. She hits return and the design is done. The Venable system will even specify standard values if desired. She now knows exactly which parts to install to have a perfectly optimized loop. And the Venable system made it possible. But that's not all. With the Venable system, stored data is available for post-processing if desired. The included word processing program further enhances the versatility of the Venable system. The Venable system is capable of providing modeling and component measurement. Another Venable exclusive is more than 100 dB of dynamic range, enough to handle virtually any situation. For versatility, Venable features sine, triangular, and square wave analysis to handle future technology as well as today's. CRT displays are in real time with menus. In addition, Bode plots can be displayed on any dual-channel oscilloscope with simultaneous display of gain and phase. For product development, the Venable system designs, optimizes, and gives the right numbers to the engineer the first time, every time. That means a system that will design as well as model. In the outmoded iteration method, designing had to be followed by modeling, followed by prototype, followed by testing, followed by analysis, followed by redesigning, and on and on. The new method, the Venable method, cuts away the wasted time, the wasted effort, and the drudgery, and provides a direct path to the desired result. If you still need convincing, look at this list of satisfied customers and listen to what some of them have to say about the Venable system.
Willarco is in the cutting edge of the military and space electronics business. We design and manufacture power conversion and regulation equipment for the military and for space. In the old days, we used to try to stabilize our control loops by using trial and error, brute force, or hand taking data. All of these techniques were really not very useful, especially taking data by hand because of the enormous amount of time involved in taking that kind of data. Just trying to read an oscilloscope and trying to pick out a low-level signal in a highly noisy switching environment was just impossible. From all the effort that that we took, and from the many hours that Dave Middlebrook and I used to spend trying to take this data, usually the result was a very incomplete and single Bode plot. From this plot, we would try to stabilize the system and come up with a producible piece of hardware. The computerized equipment that's now available from Venable Industries and that we use to stabilize all our loops has done away with all this drudgery and all this hard work and all these late hours. Well, not all the late hours. And we find now that we really can't do without it. All of the new designs that we use, do, are stabilized using the Venable system, and all of the reports that we provide to our customers on the stability of the new equipment that we design includes Bode plots produced on the Venable system. The pickup of low-level signals from very noisy switching environments and the smoothing and processing of the signal data into highly readable graphs has been a godsend to our company.
One of the most impressive features about the Venable Model 250 is it is so easy to use. Anybody could use it. When we first got our system a few months ago, we were kind of scared to use it because it's a pretty formidable looking computer system. But then after a while, I had to go down and use it, and it was so easy. I didn't even need the owner's manual. The only thing I needed it for was to hook my circuit up to the computer, because then it made it really easy. I didn't even need it to run the program. All you have to do is turn the computer on. The prompts are right there. It couldn't be any easier. Another thing I really like about the computer program is that there's no complicated added extras that you would never need to use. Everything there is essential, and it's to the point. Nothing that you wouldn't need to use, and because of that, you can leave the program if you have to go away on business for a couple months, come back, and you could just go right back to where you left off without having to do any fresh up. Well, one important thing about the keyboard is that you can control some of the functions directly from the keyboard while the program is running. Like these arrow keys can change the frequency and the voltage while you're taking your frequency response of the power supply. I like it also because it is so versatile. You can take so many different measurements. It's pretty much unlimited on what you can use it for. You can measure the ESR of a capacitor. What we often do at work is take our power supply apart, measure each part separately, and see how that correlates with the theoretical. Then we add them all together and see how that correlates with the overall. And another thing that the program has is K-factor built right into it. That is really nice. All you have to do is turn the computer on, press K, it goes to the K-factor. You press the K-type that you want, then you input a few of the variables that you need, and then it outputs all the values of resistors and capacitors for your compensation, and it couldn't be much easier. One important thing about the graphics is the way it's plotted out. It's so easy to read the gain margin and phase margin right off the plot. You don't need any calculator, any ruler to try and subtract phases, and it's just, you can just look right at it. There it is, right in front of you. It's just really easy.
In the last few years, our customers have become more sophisticated as far as stability analysis is concerned, and many of them are requiring that Bode plots be provided with prototype power supplies. It used to take a number of days to run a Bode plot. Now, with the Venable system, it takes less than 15 minutes. It's very easy to train the technicians to operate it, and most of our technicians do operate the machine. It has the capability of pulling very small signals out of large noise environments, and the machine paid for itself in less than 6 months. The machine is now vital to our engineering operation.
And with Venable, there's a very big plus: technical help and backup. With each new Venable system, a videotaped step-by-step user's guide is available, along with the concise, easy-to-follow written manual. This puts more people in touch with its many, many capabilities, streamlining R&D and testing. That's our story. You've seen what our system can do. You've met some of our customers, and you've seen the system operate. And it should pay for itself quickly and keep paying for itself over and over while it enhances your productivity and profitability. Engineers will appreciate being spared from boredom and drudgery and given the freedom to do what they were trained to do. Once you have the Venable system in your shop, you really will wonder how you ever got along without it. There's absolutely nothing else in the world like it.